I want to thank everybody for joining us today. Today's presentation is high performance actuators, types, and functions. So these are instrument grade actuators. We're going to talk about encoders, drives, and then alternatives if instrument actuators isn't for you. Okay, so we have non-captive. This is where the nut is in the middle of the motor, the screw goes right through the middle of it. We have customers that make complete gantry systems where the motor is actually moving on the screw. Some customers actually do multiple carriages moving on the screw. Now that's our part number is LA on that part. The LGA is captive, and that's really good for, it's a short stroke. And we've got some customers that are doing Z travel, some of them that are attaching a needle directly to this and just driving down into a vial, or maybe not a needle, but picking up a sample and moving it somewhere. So that's the type of application that we see with that. The external, the LSA, this we put a nut on the shaft. So the motor shaft is the, essentially the screw. We put a nut on the shaft, and if we stop everything from rotating, either hold the nut from rotating with a bearing, we create linear motion. So this is actually really good for Z applications. When you've got a fair amount of travel for a Z application, motor sits up top or at the bottom, and you create linear motion. Also, sort of a traditional slide setup where the motor's mounted to one side. So it depends what works for your application. Okay, take a look at the non-captive actuator. Again, the screw runs right through the middle of the motor. There's a molded nut on the inside. It's molded in, it's not, the threads are cut after the fact. So it's molded in, and then we cut the threads. So we've got a stepping motor, and like I said, the internal nut, essentially a hollow shaft motor. And with a linear bearing, we can create linear motion. We'll show you the animation. Now this can be reversed. Like I said, the motor can be the portion that's moving, and you can hold the nut still, and that's actually very common. Hold the screw still. All right, captive actuator. Now this is actually the guts of a non-captive motor. You see the screw here that goes through the center of the motor. We have an anti-rotate bearing and a bushing at the tip of the nose. So in this application, you want to be careful of, putting radial load on the shaft, because it is just a bushing. So in the example where you're picking up stuff, you're not putting any load on that. We also have customers that use these for things like a simple diverter or something along those lines. Show you the animation of how that works. So again, you see the heart of it is the exact same as the non-captive. And then the linear bearing, anti-rotate. Very good. External. Again, the motor shaft is the screw. And so we've got a nut that's on the shaft. We create linear motion with that. Now we look at this here. Now this is actually very common. I've never seen any applications where the motor moves. This is just by nature. The end of the shaft does not need to be supported. Although if we customize it and you go with a really long shaft, then it should be supported, because I've seen applications where you can pick up resonance, especially depending on how you're microstepping the motor. You can pick up resonance in the screw. And so I've seen customers where, a couple feet of travel and the screw actually starts to sing. And, they put a top bearing on it, and that issue goes away completely. So that's something to be aware of. All right, so for the external screws, we have there are two different types of nut here, three different types of nuts really. We've got our zero backlash. So by its very nature, these nuts have backlash, and we've got zero backlash nuts. Now this is one that we're showing you. We have a couple of different nut styles, but this has a axial spring, and so it's two nuts that are being pushed apart. We also have nuts with rotary springs that twist the nuts apart as well. All right, and you'll see here the different types of material. We'll talk about this next slide. All right, so we're in the process of changing from peak to pump. And it's really simple to see why. You know, better price, longer service life, less noise. What more do you need to know? So the again, we see here that the zero backlash, and we talk here that you do sacrifice life when you go to zero backlash. So that's something that needs to be taken into account. All right, so we manufacture all of our screws, and we're manufacturing Acme and trapezoidal screws. You know, in theory, there's really not any difference between these screws. It's just all of our trapezoidal are metric, and Acme is actually a mixture of metric and imperial. So when we talk about lead, it's the distance traveled in one rotation. So in our manufacturing, you know, all of these go through 100% QC inspection before they get shipped out to you. So let's talk about backlash. You know, in the industry, we talk about axial backlash, and so we need to understand that. Now, this is just an example. Every screw, every nut has a different, depending on the pitch, has a different backlash number. But you can see here that this isn't a cumulative number, it's plus and minus. So if you're reversing directions, it's double that number. So keep that in mind. All right, so for lead screws, something to take into account is, you know, a lot of people size them up and say, you know, I don't need to go very fast, so let's go with a really fine pitch screw. And that actually costs you life. And so that's something to take into account, is that the higher pitch screws have longer service life. You know, something else really, really big is the self-locking. So if it's a higher pitch, it's got more friction and it has self-locking. So we do recommend lubricating the screws. We have customers that put it into a monthly maintenance. You know, some put it into bi-yearly maintenance to lubricate the screws. It depends how much they get used every single day. And you see here that it does reduce self-locking effect. So that's what we're going to talk about next. So self-locking. In a vertical application, self-locking is important because you don't want the load to drift. And so in this case, you know, we can look at the formula where we're talking about friction, you know, the angle of the actual thread itself, you know, the pitch of the thread, the diameter. You know, we can solve this formula, or a simple rule of thumb is 1/3, less than 1/3 of the diameter. All right. Now, if you tell me that, well, you know, I want to use this in a vertical application, but I'm not going to be under 1/3, we can always put a brake on the back of the motor. And so that's another option if, you know, if you need it to lock. So there's ways around everything. We can customize the screws for you. We have customers that buy specific lengths, specific drawings. You know, that you give us a drawing for us to customize, and so we can build it to your exact needs. All right, thrust. So we give you the thrust on all of our motors. What we don't give you is torque. But here's the thrust calculation, and then here's the torque calculation from thrust. Now, if you want to know what is the torque of the motor, we'll calculate it for you. I'm not sure we put efficiency on everything. So we'll calculate that for you and tell you what the torque is. It's a very common question I get. As we're looking at this video, we're using a captive actuator for the claws to pick the product up. And then we're using an external for the Z-axis. Then we've got some other products that we sell. We've got a PD2C here. We've got a NEMA 17 motor turning the turntable. I want you to listen to how quiet these motors are running. We're not actually microstepping these motors. All of the drives here are programmed, and drive number 1 synchronizes to start all of the drives simultaneously. Okay. One more video. So again, listen to the sound. You're not hearing the traditional microstepping sound. So again, these are all programmed drives, and they're all synchronized off motor 1. We're running these drives. We have encoders on all of these. We're running these in FOC servo, which is why they're so quiet. Oh, I forgot to mention that we communicate in CAN open. So on both of these videos. So we're using CAN open to actually synchronize the start of the programs. So again, you see our CL3E, the LGA captive, NEMA 14 motor, NEMA 11, I'm sorry, and an encoder. All right, so we talked about a little bit about encoders as we watched those videos. Let's take a peek at encoders and why that's important. Remember, these are instrument grade, and magnetic encoders are best. And so when we look at the LGA would have a hole through the back of the encoder, so magnetic is best. Again, these are for instrument grade. This is not industrial grade, and so you can't put these out in a really dirty environment. The NEMA 8, 11, and 14, currently we have an optical option, but in a couple of months we'll be releasing a magnetic encoder for those as well. The LGA, same thing. Magnetic is best because of the rear shaft coming out, or the screw coming out the back. And again, same story with the NEMA 8, 11, and 14. We have an optical today. Now the LSA is a standard stepping motor. So in this case, we can put any encoder on the back of it and seal it to the motor. Right, so we saw the CL3E in the 2 videos that we watched. And the CL3E was doing FOC servo control of all of those motors. We also, in the same category, have our CL4E. So we've got our CL4E-1 and -2. In this case, the CL3E and the CL4E-1 would be appropriate for the size motors we're talking about. So with these drives, they can drive any of the actuators we looked at today. We can microstep, we do step and direction, any resolution. Now, why is that important? Because if you have a machine and you're not happy with the sound, with the vibration, with maybe the heat of the stepping motors, we can change all of that for you, deliver the performance we showed you. And if you're running step and direction, you don't have to reprogram your controller. You can put the step and direction in, we can accept it and improve your performance from there. So we microstep with a pure sine wave. We also have that we can Hall drive, sensorless velocity, or FOC servo. Now that's with encoder feedback. So that's actually commutating the motor. All right, these drives all have CAN open and Modbus RTU as well. All right, you see the PID servo loops, velocity, torque, and position, so we can do stall applications as well. All right, so here's the specifications on these drives. So in this case, 3 amp 6 peak, we've got a 3 amp and a 3 amp 6 peak in the CL3E as well. All right, at the beginning, I told you that if these weren't for your applications, we have an alternative, and we make smart servos. And so we do servo steppers as well as brushless servos. So the servo stepper has ranges from NEMA 17 with a 0.5 Newton-meter of torque to 9 Newton-meters of torque in the NEMA 34. So we can direct drive ball screws or belt drives. And we've got, as you see, CAN open, EtherCAT, Ethernet IP, Modbus TCP, so several different field bus options. Now, if you need to go faster, we've got brushless servos as well. And so again, the same field buses, the brushless servo doesn't have the same torque as a stepper does. So 0.12 Newton meters up to 1.7 Newton meters with our 80 millimeter brushless. Okay, does anybody have any questions?
Hi, Mike. We had a few questions chatted in during the presentation, and also just wanted to let everybody know that in the chat function, you can still ask questions, and we'll try to answer as many as we can today. So the first one that came in was, could you explain what microstep with a pure sine wave means?
Sure. So we microstep. So traditionally, microstepping, you literally are stepping the voltage or the current to the motor, and so that you're essentially taking a sine wave and you're stepping it through a sine wave into the step motor. We actually put in a pure sine wave, so it's the smoothest performance you can get out of a motor. And so, historically, we started with full stepping at 200 steps per rev. A lot of our competitions at 20,000 steps per rev. We've taken it as far as we can go with a pure sine wave. So it's the smoothest, quietest performance we can deliver.
Okay. The next question that came in was, what does FOC stand for and what does it do?
Oh, okay. So FOC is field-oriented control. And that is essentially servo, where we're commutating the motor with PID tuning. So it is the next step beyond microstepping with a pure sine wave. And so when we microstep with a pure sine wave, the motor is smooth and quiet. But when you FOC servo the motor, it gets even quieter. And so it's the next step basically in quieting everything down. It also gives us the ability to dynamically respond to the load, so that we're only delivering the current you need, so that when you're not having any demands on the motor will sit there, basically at ambient temperature. And okay, next question.
Okay. Next question is, can a non-captive motor be used for a vertical application?
Absolutely. So I mentioned we can customize. We do have customers that use non-captive motors, and I apologize, I did sort of focus on the LGA and the external, but absolutely a non-captive can be used in a vertical application. We can put a brake on the back of it if it doesn't have, if it's not self-locking. And so absolutely. You also, as I mentioned, some of our customers will put multiple motors attached to the actual carriage. And so you could have multiple carriages stacked vertically and control those all individually as well.
That was the last question that was chatted in. If anybody else has any other questions, we could stay on for a few minutes and answer those if they'd like to chat them in.
All right, thank you, everybody. I appreciate you guys attending. And like I said, if you have any other questions, type them in now. If not, I appreciate the time you gave us.